Acid rain formation, a chemical perspective. Why does rain sometimes damage forests, kill fish, and slowly eat away stone buildings? The answer lies in invisible chemical reactions taking place high in the atmosphere. Rain is normally weakly acidic, with a pH of about 5.6. This natural acidity comes from carbon dioxide dissolving in rainwater to form carbonic acid, CO₂G plus H₂OL equals H₂SO₃ This weak acid does not cause significant environmental harm. Acid rain, however, contains much stronger acids and can have a pH as low as 4.0 or even 3.0. At this acidity, rainwater becomes chemically aggressive. Acid rain refers to precipitation containing sulfuric acid, H₂SO₄, and nitric acid, HNO₃. It can occur as rain, snow, fog, or dry acidic particles. Acid rain does not fall directly from pollution. It forms through a sequence of atmospheric chemical reactions. The process begins with the emission of acid rain precursors, mainly sulfur dioxide, SO₂, and nitrogen oxides, NOx. Sulfur dioxide is released from coal-fired power plants, industrial smelting, and diesel engines. Nitrogen oxides are produced during high-temperature combustion in vehicles and power stations. Once in the atmosphere, these gases undergo oxidation reactions involving oxygen, sunlight, water vapor, and highly reactive oxidants, such as the hydroxyl radical, OH. Formation of sulfuric acid. The oxidation of sulfur dioxide occurs in several steps. First, sulfur dioxide reacts with the hydroxyl radical, SO₂G plus OH, HO₄. This intermediate is further oxidized to form sulfur trioxide, HO₄, plus O2, SO3 plus HO2. Sulfur trioxide then reacts with water vapor, SO3G plus H2OL, H₂SO₄ This produces sulfuric acid aerosols suspended in the atmosphere. Formation of nitric acid nitrogen oxides also undergo oxidation reactions. Nitrogen dioxide reacts directly with hydroxyl radicals, NO2G plus OH, HNO₃. This reaction produces nitric acid, which dissolves readily in atmospheric water droplets. Together, these reactions convert gaseous pollutants into strong acids through oxidation and photochemical processes. Once formed, sulfuric and nitric acids can remain in the atmosphere for several days and be transported over long distances by wind. Eventually, they return to the Earth's surface through deposition. Wet deposition occurs when acids dissolve in rain, snow, fog, or sleet. Dry deposition occurs when acidic gases and particles settle on surfaces and are later washed into soil and water by rainfall. The environmental chemical impacts of acid rain are extensive. In soils, acid rain lowers pH and causes leaching of essential nutrients such as calcium and magnesium. Ca2+ soil. Ca2+ leached. At the same time, acidic conditions increase the solubility of aluminium, Al, OH3S, plus 3H+, Al3 plus AQ, plus 3H2OL. Aluminium ions are toxic to plant roots and aquatic organisms. In aquatic systems, acid rain lowers the pH of lakes and rivers, leading to biological stress and reduced biodiversity. Acid rain also damages vegetation by disrupting leaf chemistry and reducing photosynthesis. The built environment is affected when acids react with calcium carbonate in limestone and marble, CaCO3S plus H₂SO₄, CaSO₄ plus CO₂G plus H₂OL. This reaction causes the gradual erosion of buildings and monuments. From a chemical perspective, acid rain involves oxidation reactions, acid-base chemistry, changes in pH, increased metal solubility, chemical weathering processes. Understanding these reactions has led to effective pollution control strategies, such as reducing SO₂ and NOx emissions through cleaner fuels, catalytic converters, and emission regulations. In summary, acid rain forms when sulfur dioxide and nitrogen oxides undergo oxidation in the atmosphere, producing sulfuric acid, H₂SO₄, and nitric acid, HNO₃. These acids are transported through the atmosphere and deposited onto land and water, where they disrupt environmental chemical balance. Understanding the chemistry behind acid rain is essential for protecting ecosystems and managing air pollution.